Okay, now we're going to take some derivatives in a way that you're not accustomed to, but we're going to start with something you're familiar with. Derivative with respect to x of fg, where f and g are functions of x, is derivative of f with respect to x times g plus f times the derivative of g with respect to x. Now, what if we take the derivative with respect to x of xy, where y is considered to be a function of x? Then it's like, here's your f function, that's just x, f of x is x, and here's your g function, g of x, well, it's now a y of x instead of a g of x. The product rule still holds, so our derivative is the derivative with respect to x of x times y plus x times the derivative of y with respect to x. Now, the derivative of x with respect to x is just 1. So we have here the derivative of x with respect to x times y is just 1 times y. Well, that's just y, and that's what we get from the first part of the product rule, the derivative of this multiplied by this. The second part is this multiplied by the derivative of this, x multiplied by the derivative of y with respect to x. Now, derivative of y with respect to x depends on what y happens to be. We don't know. So the best we can say is, well, that's just x times dy dx. We don't know what dy dx is, but whatever it is, this expression y plus x dy dx is our x derivative of the product function xy. Applying the same idea to the derivative with respect to x of x squared y cubed, we have the derivative with respect to x of x squared multiplied by y cubed plus x squared times the derivative of y cubed, x squared times the derivative with respect to x of y cubed. Now, what's the derivative with respect to x of y cubed? Well, that's a chain rule question. We're taking the derivative of the cube of some function of x. So the derivative with respect to x of y cubed is the derivative with respect to y of y cubed times dy dx, which is 3y cubed times dy dx. Now, another way to say that, and I've kind of inserted that over here, we're taking the derivative of y of x cubed. That's what we mean by the derivative with respect to x of y cubed. The prime means derivative with respect to x, and I've written it out with the prime to save space, and also because you're used to writing it that way. It's the derivative of our y cubed, y being a function of x, so I've written it explicitly as a function of x. Okay, well, in this case, your function f of x is y of x cubed. That's a composite of f of u equals u cubed with u equal y of x. Okay, so if u equals y of x, then f of u is y of x, f of y of x, which would be y of x cubed, and that's our function f of x. Our f prime of u function is, excuse me, then 3u squared, where the prime here is with respect to u, and we've got to be a little bit loose with our terminology. And I just say this to show you that this is just an application of the chain rule, and of course you have to be very familiar with the way we've done the chain rule to understand what I'm talking about, and hopefully you've done the assigned problems and applied the chain rule carefully so you know exactly what we're talking about here. So this is, again, an f of u equal an f of u with u, an f of u, I can't say it right, an f of u equal to u cubed, where u equals y of x. So that, again, our f function is then y of x cubed. Now, applying the chain rule, we got to have our, excuse me, I have a little trouble with allergies here. Excuse me, I got to stop for a second. Okay, our derivative of f of y of x is then going to be y prime of x times f prime of y of x. Y prime of x is just y prime of x. That's our dy dx. And our f prime of y of x, well, f prime of u is 3u squared, so f prime of y of x is 3 times y of x squared. So our derivative is 3y squared, suppressing the x, the y of x notation, and just expressing y of x as y. We get 3y squared multiplied by y prime. And we could also say that's just 3y squared dy dx. Okay, so back here, a derivative with respect to x of y cubed is 3y squared times dy dx. And the dy dx comes out of the chain rule. We can either think of this as taking the derivative with respect to y of y cubed times dy dx, as we did here, or we can go through the other version of the chain rule and get the same thing. The big point is that when we take a derivative of a function of y, we can take the derivative with respect to y and then multiply that by dy dx. Okay, now our first term here, derivative with respect to x of x squared is 2x, so we get 2x times y cubed. We have x squared times the derivative of y cubed with respect to x, so that's x squared times 3y squared dy dx. We can apply that to an equation. If we take the derivative with respect to x of both sides of this equation, what do we get? We get the derivative with respect to x of x squared, that's here, minus 2 times the derivative with respect to x of xy. That's from the negative 2xy. And that's going to be equal to the derivative with respect to x of 8. Now, derivative of 8 is 0. The derivative with respect to x of x squared is 2x. And the derivative of xy with respect to x, as we saw, actually, we did see that right here, is y plus x dy dx. So substituting that for the derivative of xy, we have this. Distributing the multiplication by negative 2, we get this equation. And this equation is easily solved for dy dx. We're going to just put the, we're going to get a 2y minus 2x on this side, and then we're going to divide that by negative 2x. That's going to give us negative y over x plus 1. So we know that dy dx is negative y over x plus 1. Now that's not the same expression we got down here. We have y over x here. If we take this y and divide it by x, and then add 1, we do get this expression. But we don't need to do that. I just wanted to illustrate that we could take the derivative of both sides, and having done that, we can get an expression for the derivative of y with respect to x in terms of y and x. So that if we know a value of y and a value of x, we can calculate the derivative. That's not as good necessarily as having the closed expression for the derivative, but it is progress. It is useful, as you're going to see.